So as we know, the satellite positioning principle is based on the observations made to the satellite. So at a receiver position, we observe a satellite, and the satellite distance, or the distance at a time, for example, will be measured. So it is included here by rho. So the rho is, as you can see, is a scalar value of the difference between the satellite position and the receiver position. So, and in this equation, as you can see, I need to make a measurement to the satellite, and I need to determine my position, my receiver's position in a coordinate system, and this coordinate system center is, as you can see, is a geocenter. And the rho s is the satellite's location vector, and this vector must be known, and thus I can, by using the adjustment principle or the parameter estimation principle, I can easily solve my receiver's position. So for this purpose, the satellites should send two types of data to the receiver. By the way, GNSS systems are one-way systems, which means that the satellites emit signals and the receivers capture these signals at their locations. So that's why a one-way system. For example, in electronic distance measurement, you send a signal to a reflector and you get the signal back at your instrument. So this is a two-way system. So in comparison to this two-way system, satellites only send data to the receivers. You as the observer have no contact to the direct contact to the satellite. You only track the satellites in the sky by using your receiver. So during this track, you always obtain the satellite's positions. So these positions are included in a navigation file. And also you carry out measurements. So you can measure the distances between the satellites. So there are two measurements made by the receivers, and the first one is the code observations, and the second one is the phase observation. So in this lecture, we will deal with the measurement of these two important variables captured by a GNSS receiver. So as we said, so GNSS signals are one-way signals, or they are sent to the Earth, and the receivers access, or receivers obtain these data by the antennas. And the GNSS signal in the space will be generated by the satellites, and the satellites, the system electronics, enable to produce a signal, and this signal is a modulation of three signals. So the modulation will be denoted by this specific sign here, and we have three layers here. That in the first layer is, as said, we need the satellite's position, satellite's coordinate in a geocentric reference frame. So these coordinates are sent to the receivers, or to sent to the Earth surface, and the other two layers consist of the code layer and the phase layer. So the code layer is the measurement layer normally. So by using this code layer, you determine the direct distance between the satellite and the receiver, and the carrier frequency or the physical layer is needed because you need to send your signals, your navigation data signal, so given here data link layer, and also the code layer to the receiver. So in order to send these two data, navigation and code data to the receivers, you need a high frequency or low wavelength signals, so that you can easily send the signals to the receivers. So all of the global navigation satellite systems consist of these three layers, and these three layers are modulated here and will become a unique signal, and this signal will be sent to the receivers, and the receivers then later capture this signal from a specific satellite and demodulate again. So the modulation and demodulation means the reverse. So in the first case, in the modulation case, you add up all these three signals in an electronic mechanism, and after that you send this signal to the receivers, and the receivers get this signal, after that demodulate. So which means that the receivers separate all these three layers into unique unique observations. So let's now show how code measurements, or the so-called pseudo-range measurements, are carried out on an example. So for example, all satellites send specific signals or code signals to the Earth's surface, and these signals are specific because they are not the mathematically perfect sine or cosine waves. These are special signals, and these signals are also known by the receiver. So the satellites generate this signal and send to the receiver, and the receiver has also a replica of this signal. As you can see, the structure at the satellite and the structure at the receiver is the same. So if you look at the highs and lows at the signals, you see that they match together. So the satellite sends the signal at T1, for example, and the receiver gets this signal at a later time, of course, at T2. So at T2 will be captured by the receiver. So if I have the replica, so as you can see here, the replica, then I shift this obtained code by the satellite, and I shift this signal. Okay, so this signal arrived at the second signal arrived at the receiver, and on this satellite I make a comparison. So I shift this signal on my replica signal. So, and by this way I can find where when the satellite here has sent this signal. So I can find the T1, as you see, the T1 location, and thus by finding this T1 location, I can easily compute the travel time between the satellite and the receiver. So by easily subtracting T from T2 or T1 from T2, so then the delta T can here be easily obtained. So if I scale this delta T by the velocity of light, because the signals have a speed of the at the velocity of light, so then I can get the distance between the satellite and the receiver. So in this way, I can carry out pseudo-range measurements. Let's look at the modeling of mathematical modeling of pseudo-range measurements. So why do we call these measurements as pseudo-range? So pseudo-range measurement is denoted by capital P here, and the rho is the geometrical distance. So this means the receiver obtains the satellite sent by the satellite, and the satellite emission time is denoted by Tk. As you see, K is superscript, so this denotes the satellite, and Ti subscript denotes the receiver reception time. The reception time is always larger than Tk because you receive the signal later at a later time. So if I obtain the signal at Ti, and if I subtract Tk, the satellite emission time, and multiply this by C, I can obtain directly the distance, the geometric distance. But both satellites and the receivers use clocks, and these clocks are not perfect. So these are human-made, and that's why they are not perfect. So satellite clocks are atomic clocks. That's why they are better than the receiver's clocks, but still you have errors. That's why we talk about the satellite and receiver clock errors, and these are denoted respectively by DTK and DTI. So the first one is the satellite clock error, and the second one is the receiver clock error. As you see here, normally you measure Tk and Ti, okay, and this Ti and Tk time measurements are made by the receiver, and these are there are errors included in these time measurements, as you can see, because the clock errors are available. So then I made some corrections here. As you see, these are measurements. I correct these by DTK, and again here the measurement Ti, I add DTI. So in this way I can obtain the true emission time at the satellite. So be careful, true emission time, and here true capture time or true access time at the receiver. So then if I put as you can see here, this T instead of Tk here, TRK minus DTK, for example, here, and instead of here Ti, I put DTI, or sorry, TRI minus DTI in that way, and put these into my equation. As you can see, the new equation is obtained. So normally these are, so the first term is the true true reception time by the receiver and through emission time by the satellite. So this means that this is normally the geometrical distance. So the rho term will be here. But as you can see, the equation does not include only the geometric term. It includes also the satellite and receiver clock error terms, as you can see. So that's why I cannot talk about the pure geometrical range or distance. So that's why denoted as pseudo range. So the pseudo range are measured because the satellites and the receivers have not ideal or perfect clocks. So for this reason, we instead of geometric measurements, we obtain pseudo range measurements in the GPS or GNSS receivers.